All right, I want to thank everyone for coming out this evening to this wonderful event hosted by the Sanford Underground Research Facility, our deep talks for the month of March. We do have a few more chairs up here. If there's a couple more people that want to trickle in, there's two more right up here. Feel free to come right in and fill these up as we're going, as we're just getting started. My name's Mike Ray. I'm the communications manager here at Sanford Lab. Can everybody hear me okay? I heard a couple folks say that the sound wasn't so good. I want to make sure everybody can hear me. If you can't hear tonight, raise your hand and let me know. Let me know if it gets too loud, okay? Or too quiet. Thank you. And this microphone, as you can see, won't work if it's out here, so I have to hold it right in here. Yeah, that's part of it. Yep. I did 25 years in radio, and every microphone is different. So I'll do my best, but don't hesitate to holler. Again, my name is Mike Ray. I work in communications here at Sanford Underground Research Facility. I want to thank everyone for coming out. This beautiful crowd tonight, as March is going in like a lamb. It's wonderful to be here. We have an amazing talk in store. Colossal, Caverns, an in-depth discussion of the DUNE Excavation with Michael Gemelli and some other special guests from Fermilab. We're going to give them a proper introduction here shortly, but first, we need to thank our sponsors, the folks who make the free beverages and free food, and to do that is Michelle Kane, the director of the Surf Foundation.
Thanks, Mike. So, how many of you are here for the first time? This is your first Deep Talks. I want you to stand up and I want everyone to or you can just raise your hand. Just give everyone a round of applause because this is where we hope that you're going to connect with others, discover new ideas, and mostly to leave being inspired by learning about science. That's why we're here. So our goal at Deep Talks, as Mike mentioned, is to bring scientific conversations into the public, connecting the research at SURF to our local community. And as we're live streaming tonight, we're recording to our global community. LEAD is on the map. This is where science happens, and we want you to be a part of it, as well as our global friends around the world. Topics can be related to science at SURF, but we've also included local history, we've had culture programs, and science through the arts. As Mike has mentioned, my name is Michelle Kane, and I'm with the Surf Foundation, and we are the nonprofit arm of SURF. So we support public outreach like tonight's Deep Talk, STEM education, internships, teacher professional development, cultural programming, and building intellectual community at the new Institute for Underground Science at SURF, which you'll be hearing about. So we're grateful for tonight's sponsors, which are Chris Mitchell with Edward Jones in Spearfish, and Chuck and Jolene Linkton-Wallner as steadfast supporters of Deep Talk since 2009. And a special nod to our friends at Crow Peak Brewing in Spearfish. They have been quenching our thirst here at Deep Talk since 2015, so let's give them a round of applause because I know they're going to be watching. So, extra applause. So to those of you who are joining us tonight in this room, and those who are listening to our recording or to our live stream, we invite you to be a friend of SURF. All of these events that happen because of donations, and we have a donation box on your way out if you feel so inclined, or you can go to our website and donate to the Surf Foundation. So thank you to our sponsors, and we're going to turn it back to Mike. Thanks.
Thanks so much, Michelle. Thanks again to our sponsors. That applause is very welcome to them all. I'm going to introduce now Zach Burton from Fermilab, who will introduce all of our guests tonight. Zach is a communications and community outreach person for Fermilab here in the Black Hills, so he's a great person to know here in LEAD.
Thank you, Mike. Can you hear me? Is this all right? Okay. So as Mike said, my name's Zach Burton. I'm the communications and community relations manager for Fermilab here in LEAD. One of the coolest things about my job is that I actually get to go underground and see the really impressive work that's happening right under our feet. And so the goal for tonight is to invite you all underground so that you can see it too and be a part of it. And we hope that you'll like the footage that we have prepared for you. Before we get started though, I want to introduce our presenters here. First up, you'll hear from Michael Gemelli. He is our project manager for the construction of the Farsight conventional facilities. Mike has more than 30 years of experience leading and managing both domestic and international projects, serving in project management, engineering, construction, and maintenance in the oil, gas, petrochemical, power, and metals and mining industries in the private sector. He holds a Bachelor of Science in Aerospace Engineering and a graduate certificate in construction management from Illinois Institute of Technology. Welcome, Mike. Next up, you'll hear from Ryan Moe. Ryan is the U.S. General Manager for Tyson Mining, and he's responsible for all U.S. projects that Tyson is involved in. He has over 25 years of experience in project execution in both the mining and defense industries. In the mining industry, he has been fortunate to hold varying positions in operations, administrations, and managerial roles. He has a bachelor's degree from Indiana University, my alma mater, with additional certificates in material management and government procurement programs. And last but not least, you'll hear from James Rickard, who is the resident engineer supervising the cavern excavation in Leeds, South Dakota for the Long Baseline Neutrino Facility Deep Underground Neutrino Experiment. James has a degree in mining engineering from the Camborne School of Mines in Cornwall, UK, and a master in arbitration and dispute resolution from the City University, Hong Kong. He's gained 30 years of international experience in managing large-scale, complex underground projects with extensive knowledge of various tunneling methods in different ground conditions. Also has extensive explosive engineering experience in both underground and open cut blasting. So if we could just give a round of applause for our presenters for this evening. And I'll turn it over to Mike Gemelli. Mike.
All right, well, thank you, Zach. Let me get this microphone all set up. I have a tendency to talk with my hands, and at the same time, I'm having to advance these slides. But I'm hoping I can deliver this presentation with the same energy level that you heard from Michelle, which may be a challenge. This is towards the end of the day. But I want to thank everyone here, particularly for the introduction, and I want to say good evening to everyone here that's in the Visitor Center and those who are actually streaming this presentation live. When SURF extended the offer to host tonight's discussion, it was a challenging one because how do you take 3.5 years of successful project execution and summarize it in 1 hour? So we took that challenge on, and I hope you guys are well pleased with the tonight's presentation. So we'll start out with the agenda. So we've already gone through the welcome and introduction. What I plan on doing for our Deep Talks discussion is we'll start out with a brief overview of the LBNF DUNE project. Then I'll provide an update and status on the excavation activities to date, followed by a discussion led by Ryan Moe, who happens to be the U.S. General Manager from Tyson Mining, who's here with us today. And he's going to highlight some of the underground completed achievements through both pictures as well as videos. Next, James Rickard, who's our resident engineer from Arup, will do something similar to that. He's going to walk us through the vast underground spaces 1 mile below the surface through a narrated video. So he's going to do that as we watch the video. And then last, we'll open up the tonight's discussion for any type of Q&A questions you may have on what's going on underground. So with that being said, we're going to jump into the first item on the agenda, which is the LBNF project. So a lot of folks often ask, what's going on underground? You know, and what kind of experiment is this going to be? And it can be summarized in 2 main points. The first one is the Deep Underground Neutrino Experiment, also known as DUNE, or abbreviated as DUNE. It's a game-changing experiment for neutrino research and science and has the ability or the potential to transform the understanding of the universe. Secondly, the Long Baseline Neutrino Facility, also known as LBNF, is the infrastructure that's going to make it happen. So collectively, the LBNF and DUNE project is the first internationally conceived, constructed, and operated mega-sized project that's hosted by the Department of Energy and happens to be the largest project the Department of Energy has ever done. It's also worth pointing out for everybody here in today's audience, as well as those who are streaming in, that this project, the LBNF DUNE project, has more than 30 countries actively participating in this project with more than 1,000 scientists and engineers on board. I call this next slide the big picture. Okay, so What you see on this slide, the project is broken up into 5 sub-projects. There's the far site location, which represents Leeds, South Dakota here, okay? And there's 3 of those sub-projects actually are here and going to be built underground, starting with the far site excavation, which you're going to hear more about in this presentation. In addition to that, you've got the BSI, which stands for Building and Site Infrastructure. And then you have the FDC organization, which stands for Fire Detectors and Cryo Infrastructure. All 3 of those projects are going to be hosted here in Leeds, South Dakota. Now on the right-hand side of the screen, these are the 2 sub-projects of the 5 that are going to be built at what we refer to as the near-site conventional facilities. Okay, so that lab is the Fermilab National Accelerator Lab in Batavia, Illinois, which is a suburb of Chicago. But the 2 that you see out there is the near-site conventional facilities plus beamline, and then in addition to that, you have the actual near detectors. So from this picture, and it's a very simplistic picture of what we're going to plan on doing when we start running the experiments, but the neutrinos get launched from an accelerator located at the Fermilab Accelerator, which is 800 miles away, in a different laboratory, and these neutrinos will be launched underground, and they will be shot towards South Dakota, Leeds, South Dakota, where we're going to actually measure and see if we can detect them as they come through. It's a very simple process. They shoot the neutrinos at us, and we catch them. It's as simple as that. So there's 3 science goals that the LBNF DUNE experiment is trying to achieve. Okay, the first goal is to determine if neutrinos are the reason the universe is made up of matter. The second goal is to prove Einstein's dream, along with mine, of the unification of forces through subatomic phenomena. And third and last goal is to observe neutrinos emerging from an exploding star and probably witness the birth of a neutron star and or black hole. The picture on the left-hand side of the slide is what we're building underground, 1 mile underground at the far site location. And the picture on the right is the near site location of what the facility is going to look like in Batavia, Illinois. So again, you've got the LBNF side, the far site that catches the neutrinos, and then on the right side at the National Accelerator Laboratory in Illinois, they're shooting the neutrinos at us. So, all right, so this next slide is a picture or satellite picture of what Leeds, South Dakota looks like. Okay, a lot of people ask me, where is this experiment going to be? Well, first of all, it's underground, so you're not going to be able to see it. But if you happen to be sitting in the visitor center today, you could see that red box at the very top of the screen around, that would be about 11 o'clock. That's the visitor center, and that's where you're sitting at right now. Now, just to throw out some points of interest along the way, if you're familiar where Mill Street and Summit Street is, that's the intersection there. And just southeast of that, in that canyon along Kirk Road, and if you're familiar with the abandoned coal plant that's out there on Kirk Road, you'll see where the LBNF project is being currently built underground at this point. So now you've all been educated in high energy physics in the field of neutrino research and science. So now we're going to move on to the exciting part, which is the first phase of the far site conventional facility, which is the excavation subproject. I'm sorry? Can someone turn the lights off in the back? Thank you for that suggestion. Is that better? Okay, all right. Thank you for that suggestion. All right, so let me advance to the next slide. So this is a very high-level list of the scope of work that's going on underground for the excavation sub-project. So you can see in those sub-bullets and bullets there, it starts with the development of all the spaces underground, and that's primarily through drilling and blasting. In addition to that, the scope includes a raised bore development that connects 2 underground levels. That's the 4850 level and the 3650 level. And we're going to discuss more of that later on in the presentation. Besides that, we have the installation of the ground support, and that includes everything from rock bolts, mesh, shotcrete, and such. And every flat area that's been excavated to date will be poured with concrete. So there's the installation of the concrete floors for the drifts, as well as the caverns. And then each detector cavern, this would be the north and south cavern, which you're about ready to see, has provisions in there for anchorages for bridges, supports for mezzanines, and monorails for overhead cranes. And this is really teeing up for the next sub-project, which is coming just in a few months, probably July of this year, which is the BSI sub-project. And then last is the installation of long-term rock monitoring systems, and that's required to detect underground movement, which I think is kind of important if you're going to be working underground a mile below the surface. This also is the basis of the scope of work for TMI, which we'll see here shortly. Okay, so this is what it looks like underground. It's like a little city. So we have field offices in there, we've got break rooms, we've got maintenance rooms. It's really neat. But just walking through this slide, this is an overview of the underground excavation sub-project, and everything that you see here in gray, and I'm going to kind of use my cursor here that you see it. This is what I'm referring to in gray, is everything that's been excavated by TMI. Okay. All right. And there will be things that I'm going to point out on this slide that you're going to hear more about and see more about in this presentation. But let's start out with the easy thing, which is the Ross shaft. And that's on this far side right here. This is the Ross shaft. If you're familiar with Mill Street, you go all the way straight up to the top of the hill, and that's the Ross head frame. Okay, that's where it all starts. Basically, the Ross shaft is required for transporting personnel, material, and equipment from the surface all the way down a mile underground to what we call the 4850 level. So when you get off the cage, and you'll see this in the video, you come out on what we call the longest access drift, and this is called the south access drift that you see here with my cursor. Okay, it's approximately 700 feet long, and if you took all the little drifts and you put them end to end, you'd have approximately 3,000 feet of drifts that have been blasted, drilled, blasted, and shotcreted in the field. Now, in addition to that, some other things that I think are really neat is off to the left of the south axis drift, where my cursor's kind of hovering, is the maintenance shop. Okay, and then if you go down this here drift and you turn, if you can follow my arrow, this is the north cavern. Okay, the north cavern, and just opposite of that is the south cavern shown here, are identical in size. What you have here in the middle is what we refer to as the central utility cavern. It's kind of nested right between the north and south caverns, and we're going to go over all that in this presentation. So you're experts in underground excavation. Off to the very end of these three caverns, they're all joined with this spray chamber. Now that spray chamber is necessary for both ventilation and cooling of the underground experiment. So that's like coming up in the next phase. But off to the far right, you'll see this, where the top of my cursor is, this is the 3650 level. And then right below that is the spray chamber, where this raise or shaft joins up with the spray chamber. This is the 4850 level, so that's 1,200 feet. So level to level, one of the things that Tyson Mining had to do was to go ahead and put that raise in using a raise bore excavating type technique, which I'll show you later. But I just kind of want to point that out to you, and we've got some really neat videos to show you on that. All right, so this is what the north and south caverns, as well as the central utility cavern, look like underground. They're very big. You've got the north and south cavern, and again, there's three caverns, but I only have the two shown here. But the north and south caverns are identical in size. So essentially, they're 66 feet wide for the north-south cavern right here. They're a total of 92 feet high, so that's like the equivalent of a 9-story building. And they're 475 feet in length. Okay. Now, if you jump down to the central utility cavern, it's not as tall. It's only about 37 feet tall. It's 64 feet wide, but it's 624 feet in length. Okay, so the central utility is what gives the power to the north and south caverns. All right, so this next photo is a plan view of the underground. All right, so I'm happy to report that the excavation sub-project finished exactly a month ago today. All right, so all the cavern spaces that you looked at in the previous slides, as well as all the drifts and the maintenance shops and all that, are 100% complete at this time. The only thing that remains, and this slide is a little bit dated, is the concrete floors. If you remember, I said all the flat surfaces need to be fully concreted. So when maybe about the middle of May, this whole this drawing that you're looking at will be that same color, that green, and that green represents concrete complete. So right now, the north cavern, and I'm just going to kind of hover around that with my cursor, that's probably about 98% complete. There's just a little section in the middle that needs to be concreted right where my cursor is, but otherwise it's pretty close to being done, and it most likely will be done by next week. And that means from one end to the other end it's fully concreted. If you jump down to the south cavern, it's about 50% done on the east end of this cavern. Right where my cursor is, that should be all green. So, and again, we should be done with the concreting activities probably about mid-May. And in which case, if we were to look at this drawing, it'd be all colored green at that point. So we're only a few months away from being at the end of this project. So this next slide, I call this my fun slide. I have to be careful on how I define fun. But this is what I call my excavation factoid. So what I've compiled on one side of the slide is the left and right. Okay, you can see that. A lot of people ask me, well, how much have you excavated? How much rock has been excavated, drilled, blasted, and brought to the surface? Well, the quantity is approximately 310,000 cubic yards, or the equivalent of 820,000 tons. Now, if you compare that to something on the right side, something that everybody in this room would be familiar with, 820,000 tons is the equivalent of the weight of 8 aircraft carriers. Okay. Now, explosives consumed. A lot of people ask, well, how many tons of explosives is used? Well, that could be summarized as 560 tons. We have 560 tons of explosives were used to produce 820,000 tons of blasted rock or muck. So 560 tons produces 820,000 tons. Now, if you want to put that to something that everybody would be familiar with, and this is where I have to be very careful so I don't end up on the Department of Homeland Security's watch list, but the equivalent energy of 560 tons, that energy that's released, is the equivalent of 651,000 kilowatt hours. Now, what is that? That's enough energy to power 3,000 homes in Lead and Deadwood for a week. Okay, that just kind of puts it in perspective. In addition to that, the next 3 bullet points you see here, which is your split sets, your tread bar bolts, and CT bolts. These are different types of ground support anchors, okay? So TMI has installed, I'm going to go to the first one, if I can find my cursor, here it is. 76,000 split set bolts. They're roughly 6 feet tall, about as tall as I am. And if you were to put them end to end, you'd have the equivalent length or distance of 87 miles. That's like leaving here, driving all the way to Rapid City, and then coming back. That's the equivalent of how many split bolts have been installed. In addition to that, if you go right below that, you have 11,000 tread bar bolts. If you put them end to end, and they're typically about 10 feet long, you'd have the distance of 21 miles. CT bolts, very common in this industry, almost 17,000 CT bolts have been installed. And that's, if you use the same analogy or the same calculation, put them end to end, you'd have the equivalent of 52 miles. So we'll keep going down the list. Welded wire mesh sheets. I call them sheets. Some people call them panels. But TMI installed close to 14,000 of these sheets. And they measure, think of it like a 4x8 sheet of plywood. But these are 6 foot by 11 foot. Okay. And they have installed 14,000 of them. So if you put them end to end, side to side, you'd have enough to cover a 22-acre small farm. In addition to that, cubic yards of shotcrete applied. Okay, and you'll hear a little bit about this when Ryan talks about it in his presentation. But 12,000 cubic yards of shotcrete applied to date is enough to fill 4 Olympic-sized swimming pools. Concrete poured, and as you saw in the previous photos and that, we're still pouring concrete. We'll still be pouring concrete for the next couple months. But what we've poured out to date is about 6,400 cubic yards, and that's enough to fill 2 Olympic-sized swimming pools. And then last, as I mentioned before, we've got about 3,000 feet of drifts that have been drilled and blasted, and we have and that's a little over a half a mile in distance. So I've got a short little video, an animated video that I want to tee up for you guys. But every construction project has to have a starting point, and this project's not anything different. The raised bore was necessary to go in first for both ventilation and cooling. And I have a little animated video that'll take you through the process now. If you remember the slides, we had 2 different levels. You had the 3650 level and you had the 4850 level. Doing the math, that's 1,200 feet between each level. And a level is like thinking of it as an elevation, okay? But this is underground, okay? The process starts out with, and I'll just kind of circle with my cursor, this is the raised bore machine, okay? And it gets set up right over the target and it just drills straight through, okay? And TMI had a directional bit to keep it on its target, but it had to hit a target that's over 1,200 feet away. So with that type of accuracy, they used a directional bit that was Wi-Fi controlled to keep that bit on target. So I'm going to start that video so you can see the whole process. So a little introduction here. But it all starts out with a piece of equipment set up over the target, and you can see those are drill strings or drill stems, and they get assembled, and then they drill deep into the ground until they hit the opposite end. In this case, the opposite end is 1,200 feet away. We take the directional bit off, we put this cutter bit, and we back ream it in reverse. So again, this is how a very simple process, but a very complicated process, and to be able to hit that target with the accuracy that it needed to be was really important for this project. So this was something that TMI really shined on. Oh, okay. Sure, okay. That's good to know. Thank you for sharing that with us. She was saying that there's the same process in the homestake days. They used the same process back in the day when they were mining for gold, and there's one just like this back at the mining museum. Smaller version of it? Okay. Okay. It's 5 footer, 5 foot in diameter hole? Yeah. Okay, so this hole that what TMI had to put in, it was about 12 foot in diameter. So we'll go on to the next slide. And I'm just gonna see if I can, there we go. Oops, no, that's not what I wanted to see here. All right. Okay, all right. That was awkward. All right. So I hope you enjoyed that two-minute video because the process that we did underground actually took us 5 months. Okay. So I've got a couple pictures here. Again, I want to just hover around the 3650 level right here. There's the 3650 level. and that's where the actual raised bore is set up right over its target, and it drilled 1,200 feet straight down into the spray chamber, which is right here at the bottom. Now, the picture on the right, you'll see James Ricard standing right next to the cutter head. This is after they dropped the directional bit off and they attached the cutter head to it, and they're getting ready to back ream it to create the 12-foot diameter raise for ventilation and cooling. Right next to James is Sid DeVries. He's one of our project engineers on the project team. But this, you can see, this is the overhead section of the spray chamber, and this is where the 12-inch bit came through, broke through into the spray chamber to allow them to attach the cutter head, which now will go back up and create that ventilation raise. So again, a 2-minute video, but it took us 5 months to get there. All right, so this is my last slide, and I wanted to kind of share this with you because I get this question a lot. It was like, how, you know, you're underground, a mile underground, and you're drilling, you're blasting. How do you get the muck or the plastic rock to the surface? And it's a really real simple process, but it's very complex. It requires a lot of engineering and design. But to simplify it, I've got 2 pictures. The picture on the left is a more simplified cartoon illustration of how we bring the muck underground to the surface, where it's then crushed. You know, comes up through the Ross head frame, it gets crushed, it's put out on a conveyor belt, and then, you know, it's discharged into the open cut, which is right behind you in this, right outside that window. The schematic, on the other hand, is a little bit more intense. Essentially what happens is when you're done, you know, blasting your rock, whether it's in the drift or in the cavern, you know, we have this large mucker that comes up and it picks up all the loose rock and it takes it over to a grizzly. Now, a grizzly is nothing more than just a large sifter. It sifts smaller rocks from the bigger rocks. The smaller rocks tumble down the ore pass. The bigger rocks get caught at the top of the grizzly, where we have a rock breaker, and it breaks big rocks or boulders into smaller rocks that allows it to go through the grizzly. Kind of very simplistic type process, but it works. Now, once the ore, I should say the muck goes down this ore pass, you know, at the very bottom of this ore pass is what we call a skip. And it's waiting at the bottom, and all these rocks get loaded up into the skip. And a skip is nothing more than like a rectangular box. And so we load up this box. We typically get about 7.5 tons inside the skip, and then it brings it up to the surface. Now, inside that box, we can't, or all that muck that's stored inside that can't be put out on the conveyor belt. So at the very top of the process, we have a crusher, okay, up in this Ross head frame. I'm going to switch and I'll kind of point, here's the Ross head frame. This is where I'm currently at right now, okay? So it takes the 12-inch boulders and it breaks them into smaller bite-sized boulders that are about, or I should say bite-sized rocks that are about 3 to 4 inches in diameter. And then that allows it to be put onto a conveyor belt, and that conveyor belt takes the rock out to the open cut where it's discharged. Now, the conveyor itself is about 4,300 lineal feet, so it's a very long conveyor, and there's a number of places where you can see it gets handed off at different points, from CVO1, conveyor belt number 1, to conveyor belt number 2, then it goes out to conveyor belt 3, and then 4 is what you see out at the open cut as the rocks get discharged off into the open cut. Now, we're done discharging. We haven't been discharging for a while. Again, it's all tied to the excavation being complete. We do have a little bit of stored muck underground, which we plan on removing over the next 2-3 weeks. But then after that, won't be no more discharging to the open cut from that point on. So at this point, this is my last slide. I'm going to turn this over to Ryan Mull from Tyson Mining. Go ahead, Ryan.
All right. Thank you, Mike. So I'm going to begin with a video here. And this is a cycle of mining. How many people in here have been in mining before, have worked underground? A few? Okay, fantastic. Well, you guys will have to correct me if I say anything that's wrong, so feel free, I take that well. So this is a typical cycle of mining, and this was at another project that we did. So the video will start at the end, which is the blast, and that's where the new cycle begins. So we come in, we muck it out, that's where we take all the spoils from that blast, and we clear that out, and then get ready. And because now you have loose rock overhead, we have to support that rock. So we come in with a bolter and we install bolts, as Mike indicated, with different bolts that we've used here, as well as those mesh panels that we install to hold it. Now, real quick, we use words in mining that are a little different. So Mike has said drift. So a drift is a open ending on one end, and then it's got a heading of where our working face is. So that's the face is what we're working on. Overhead is the back, and then you have the right rib and the left rib. We, instead of using walls, right, we have to come up with our own language. It makes us feel better. So they're still bolting up here in the video, and then they'll get done shortly. And then they clean it up. Now here our surveyors are coming in, they're cleaning it up, and they're going to start marking the face or painting the face. That's where they survey it out and they find out where the next pattern is that they need to drill the holes in order to put the explosives in order to blast the next round. This is repeated over and over and over and over thousands of times in a project of this size. So now we've got a drill in here, we call it a jumbo, and the drill has got two hands that come out and they drill the pattern for you. And so we've done that. We're now having it check out. Now we're loading in our explosive material into those holes for a final cycle of the round. Now sometimes there's an intermediate part where we spray shotcrete, which is another area for ground support. And so that's the end of it. So we've loaded the round and then blast. All right. So here is a cycle that we did here at Fermi. Instead of blasting the face, we did it downhole blasting. And so we've got a video here showing that. So you can see that it's set up. What we're going to do is we're going to blast this, and you can see all the holes that we drilled. So that's what you're going to be looking for right now. And so after the blast, we also have to let the smoke clear and all that get out of there because there's a lot of harmful materials. So we smoke out and then we go in there and start the process all over again. So here's a couple still photos of the process. So you can see they're as I said, setting out the blast pattern. They're painting the face. They also will need to do some scaling to get rid of some of that loose rock. And they're doing that with our jumbo, our drill. And then the far right picture is that other phase that we used, and we used here at the Fermilab project, which is the application of shotcrete, which we sprayed on all the ribs and on the back, using that mining language again. So here's some pictures of the excavation of the caverns underway. So right here you can see those monorail beams on the top. Those were not used for the mining excavation at all. Those were used for the next phase of the project, the BSI and other phases, but we had to install those early on in the project. So the way that we approach these caverns is we start at the top. So we do a pilot drift, and then we work our way down, or we bench down. And this is that process. Well, as we bench down, our gear becomes captive. So we have to build a ramp down, and that's what you're seeing on the left is a ramp down to the base of that cavern in order to get our muck out as well as our gear. And then the picture on the right is just another beautiful view of those caverns underway. And here's a good view of the cavern as it's being constructed. We have a drill in there. Now just keep in mind, if you go out into the visitor center, you see that cage out there, or the elevator, as normal people call it, but we call it a cage, because once again, we like our own languages. And so on the cage, we had to get everything that we put underground on that cage. And so this large piece of gear had to go down through that shaft. So we had to cut it all apart and then weld it back together. We have some of the best mechanics in the industry, and they're here working on this project. And so they put that together. So every day our crews have to go underground. All of our material has to go down on that cage, same size cage. So here's a couple pictures that we have, again, of the underground. So you can see the mucking operation on the left, and on the right, they're securing that face with some bolts. And just one thing to note on this picture is there's not a lot of lights underground. Well, for us, that's normal, right? We have a cap lamp, and that's all the light you need. But for those that maybe are not familiar being underground, it's a little unnerving to some people when they get underground. And newbies, I like to take them underground and have them turn off their light. You've never seen darkness like being 20,000 feet in a drift and turning off the light. It's dark. And anyway, so you can see how it is underground. And once again, our miners, our operators, once again, we brought the best people in the industry. We brought them here to work on this project. So this is the central cavern. Once again, the utility cavern. So it's not as high, the back is not as high. So this is, on the left, you can see the concrete's already been poured. And what we did is we laid some plywood sheets in order to protect that concrete, because we moved equipment and gear on there as we continue the project forward. And then on the right, you have some gear that's parked in there. And I believe that's the 512 bolter. That's the world's largest bolter that we had to bring into this project in order to put 20-foot long bolts into the back and into the ribs. Those are those CT bolts. So imagine that, the largest bolter that exists in the world, we had to take the cab where the operator works, we had to cut that baby in half. And there's a lot of wires going through there. We also have great electricians. And so we brought them in and to help put this gear back together. And then it had to be recertified by the company that supplied it. So very long process in order to mobilize equipment in an underground environment like that. So here's a couple real wow me shots, right? This is the excavation as it's complete. You can see in the north cavern. So one of the aspects that we had to do that was touched upon was these large pedestals that we had to put in for the concrete. Those pedestals will hold the structural steel for these large tanks that's going to hold 70,000 tons of liquid argon. That's a lot. So these massive tanks will come in. Well, those steels had to go onto these pedestals. So you'd see a close-up of the pedestals, and now these little dashes you see on the side, those are square pedestals that we built in order to hold those structural steel tanks. And then you can see the floors poured. So really amazing to see. You can't see any people walking around there, but these caverns are 90 feet tall. So if you did, that person would look wee little size, right? Little leprechaun in there. So here's a good picture. You can see a person walking in the cavern. This is once again standing on the concrete, looking down in the north cavern. There are massive spaces that we built, and we're really proud of the work that we put into putting these together. Really excellent job, and I think that the quality of the work speaks for itself. And so the last excavation part that we had to do was at where the Ross cage comes down and where you get off. In order to get all that steel in there for the next phase, and these steel beams, they didn't want to weld them back together. And so they have to bring them down as large steel pieces. So we had to enlarge that space. So before, when you got off the cage, it was about 10 feet roughly in height to the back. Now it's, James, what is it, 90, 80 feet? 60 feet when you get off the cage right now. So it's really impressive to see that space has just been enlarged and it looks completely different. So that's the last pictures we have of the excavation. Once again, I just want to thank from Tyson Mining. We're really happy to be part of this project. Our staff, our leadership, our engineers, our mining crews, and our concrete crews did an outstanding job. And if you ever see a Tyson miner walking around, please thank him, because we're happy to be here and we're happy to be part of this. So thank you very much.
Okay, so for the final part of this talk this evening, I'm going to go through an underground video. Basically, we're going to show everything underground. I'm going to try and keep up with the video and narrate it whilst we're going along. Okay, so we're at the top of the shaft there. We're walking down the ramp now. You see on the left-hand side the brass board. That's where we tag everybody in, so we understand who is underground or not. Each person carries 3 tags, one to be at the top, one to be on the bottom, and then one to be on their own person. That's the cage that we've been talking about. It's exactly the same size as the cage in the visitor centre. Normally we can carry 29 personnel plus 1 cage tenderer. I think on this cage here, there's probably only about 15 or 18 people, so it can get pretty cramped, you know, when we get on there. Takes around about 10 minutes to travel from the surface 1 mile underground to the 4850 level. And when we get to the bottom, you'll see us entering the Rossbrow area just here. So the cage tenderer, he will put the cage on chairs. So basically that allows the tension to be relieved off the rope so we can offload and unload heavy pieces of equipment. Because a lot of the equipment is actually placed in the cage and then rebuilt, or sometimes it's actually slung underneath the longer pieces and then pulled out into the station. So the cage tenderer, he allows everybody else off the cage, and then they'll put their second brass on the brass board underground before going to their works area. So as we come out now, you'll see in the photo from Ryan, we'll be walking out into the Ross Station area. Total height now is 60 feet, and then it chamfers down. And this is mainly so we can get the large cryostat steel underground and easily off the slung load. Originally, this was only 10 feet high. So this was a major excavation and also close to the shaft structure. We're now walking towards the workshop, this TMI's workshop. This is where they do all the maintenance on the equipment, and also where they built, reassembled all the equipment after getting it underground. And this is where they are disassembling the equipment now to sling it back up out from underground. After that, now we continue walking towards Governor's Corner. This is basically the main intersection underground on the 4850. Going in that direction towards the north is the West Access Drift, which allows us to walk all the way over to the Yates and the Davis campus. We're now walking towards the North Cavern, and we'll enter the cavern at the west end. We have an overlook there, and then we'll be able to see inside the caverns. So as you walk toward the caverns, you can see the monorail beams in the crown and on the spring line. You see the ladder access way, scaffold access way to the left of me, and there's the guys working underground. We have some concrete slab there cast at the bottom, and then further back is the cavi drain, which is the drainage layer. This is a nice fly through with the drone showing the caverns. You can actually see all the shotcrete, which is a sprayed concrete that seals the caverns. Now we've walked down the decline. We're at the bottom. We're at the 4910 level. So this is where the workers are currently working to pour all the concrete. You can see the pedestals in the foreground and the shotcrete on the walls. And the workers there are installing the drainage layer, so any water that gets captured can go underneath the base slab and then out of the drainage system. This is a nice walkthrough with the camera showing the final base slab. Now we're walking towards the center of the caverns. This is the middle of the cavern, and eventually there will be a steel bridge be placed across this cavern to allow us to connect to the north CUC and south cavern. We're now walking towards the spray chamber. This is where we install all that equipment to remove the heat from the experiment, and at the very, very end of that chamber is that 1,200-foot raised bore. This is the central cavern, CUC. This is where all the equipment is to run the experiments, but we're using it as a storage area now. We have the concrete bags, and also we have some equipment storage. That's basically the transporter for the cement, concrete, and that is the shotcrete machine that they use to spray the concrete. We have also have 2 batch plants installed in the CUC, which we mix all the concrete and shotcrete underground. We deliver the concrete in dry super sacks. They put them in the mixer, then we add water, and then it discharges into the transmixers. And now finally, this is the south cavern. This is also the western entrance, and it's a nice overview. We can see that it's slightly behind the north cavern because this was the last one to be excavated, and doing a great job. Thank you.
We're going to open it up here to questions in just a minute. We want to ask what questions you might have for the audience. And while you're thinking about your questions, I'm going to switch microphones so I can bring a microphone around to you. We'll repeat the questions. Those who ask questions get a free gift from TMI. So there's a little extra incentive here tonight. Thanks to TMI for asking a question. Zach from Fermilab will bring that gift. I'm going to get this microphone set up while you're thinking about your questions, and we'll be ready to go. All right, testing 1, 2. We have a question right here already, sir.
I noticed on an earlier slide, there was reference made to stability of the rock after the excavation is made because earth moves. It's a living thing. And I was wondering, is the system that is used piezoelectric, where you put piezoelectric sensors and drill them into the rock, and then are they hardwired or on Wi-Fi or Bluetooth? How is that handled?
Excellent question. Did everybody hear that? Come through okay? Okay, good.
Okay, so we do have extensiometers. They're vibrating wire extensiometers. There's 4 different locations within the depth of the rock, okay? And they are actually connected to fiber optic. And then we have a data collection center underground, and then that also transmits the data to like a data capturing center, which then therefore plots the graphs to show the movement within the rock mass. Because within the rock, you know, we have those 20-foot-long CT bolts, but we don't want to hold the rock tight back against the rock. We want some relaxation because we don't want a high-pressure build-up, and that's why we have the rock to relax, and it converges slightly in the rock, and then that's when the rock bolts start tensioning and take on the weight to hold that final rock in place. But then monitoring that is through those MPBXs, the extensiometers, and there will be a few in there long-term to check for any further ground movement throughout the life of the project.
Thank you.
What other questions might be out there?
17,000 tons of argon. Where does argon come from, and how are you going to get it down there? How big are these captures that they're...
Oh.
The question was, where does argon come from? How are you going to get it down there?
All right, I'm going to give it my best shot. Okay, so yeah, the actual number is 70,000 tons of argon. So it's actually trucked here, okay, by tanker truck, and it'll be sent down the shaft through a series of some lines, and it'll be, well, it gets evaporated, it's sent down as, or it comes in as a liquid, it then gets evaporated as a gas and sent over into the actual detectors where it then turns into a liquid again. So where argon comes from, I'm not exactly sure, but we're gonna have a lot of truckloads coming up the mill stream, so.
What other questions are out there? Here we go.
The motorized equipment you're using, is it diesel or electric? And if it's diesel, how are you mitigating the exhaust and storing the diesel?
Yeah, so it's both, diesel and electric. So when it's tramming, once again, we have to use different words. When it's moving along, it goes on diesel power. And then when it stops to, for example, to drill, then it switches over to electric. But for that, we have that mass ventilation system to move that through and to keep the cycle of air. So it's, for most areas, you don't have to have a face mask, but for some of the working areas, you do have to have a face mask. And we get diesel deliveries every day.
Another question up here?
I do have a question. At the very, very beginning, you said something about you take the neutrinos from Fermilab and shoot them over here. Where do you get the neutrinos? Well, yeah, I mean, do you say like, here's neutrino number one and number two?
Anxious to answer that question.
There's a really cool video clip in the visitor center that shows how they use the accelerator and filter out those neutrinos.
Okay. All right.
So if I could just add to that, so there's an accelerator in Fermilab, Batavia, and these things are shot around many cycles times until they're shot off into a particle detector, and that's what ends up getting shot underground. So.
Fermilab was one of the first large particle accelerators in the world, right back
Correct.
in the 60s,
Yes,
70s. So we have a
is.
long history of doing this great work. Excellent questions from the audience. We've got another one over here.
So when exactly is the experiment supposed to start? Do you guys have a approximate date?
All right. So the next phase of this project is called the BSI, Building Site Infrastructure, and that's roughly about 18 months, 18 to 20 months worth of construction. And then right after that is the fire detector cryogenic portion of the sub-project, and it's roughly the same amount, 18 to 20 months. So adding it up 40 months, let's call it 48 months, 4 years from today. So we're looking at 2028, 2029, somewhere in there. So,
And I think we had another question from this gentleman right over here. Sir, go ahead.
Yeah, can somebody speak a little bit to how the experiment will actually be powered? There was some mention of the utility cavern. Is that going to be supplied underground and shipping fuel underground, or is that going to be supplied from the surface? And then additionally, can you also speak a little bit about how the volume of material being removed is fairly astonishing. How many trips does the cage need to make a shift to make that happen? That seems like a fairly significant operation.
yes, all good questions. So the first one, the power will be brought down from the surface. Okay, so that goes from the surface down to the 4850 level, and that's what powers all the experiments underground. The second part is how many cages that we would need to hoist, both material and equipment. I don't have that number offhand. I could probably look that up for you, but it's quite a large quantity. Now, we did look at it from different standpoints because we'll have multiple contractors down there at the same time. We're going to have KAJV down there working down there side by side with what we call the FDC organization, which is the fire detector cryogenic teams down there. But there's warm structures, cold structures, and then there's BSI. So there's going to be a lot of subcontractors down there and a lot of cage deliveries. But that's one of the things that we had to look at in terms of cage utilization to make sure that we didn't overtax or overuse the actual hoist beyond its capabilities or its being able to service everybody. But we're well under it. I think we're within 70% of utilization for the actual system itself. So I don't know what that breaks down to in terms of cages per day, but.
We've had some excellent audience questions this evening. Who else might have
Yeah,
one? We're just
I was
got a
just
couple
gonna
minutes.
I was just going to add a bit more. We can roughly do around about 4 cycles an hour, and then say like we get a super sack, which is about 0.7, 0.8 cubic yards of shotcrete. You can get 4 on one flatbed, so 416 an hour, and we're probably doing around about 80 a shift. So, and that's just materials. That doesn't include personnel and other drop-offs and things like that. Then you might have a fuel cell to get the diesel underground, et cetera, et cetera. So basically, once we start working, that cage is running pretty much non-stop, 24 hours a day. Yeah.
It's so good to have mining engineers who calculate all these things. Very important, very important.
Hello, my name is Debbie, and thank you for your time tonight. Mike, I think you need a far more creative name for that one drift there instead of the south wall drift or whatever. Yeah. You could call it the sad drift, because wasn't it SAD? But
we've got one of those already, sorry.
Oh, see, you got to work on that, Mike. Oh, I would go for that. Mike, on the ventilation shaft, does it suck out? Is there a big fan on top of the, James, is there a big fan?
Yeah, so, in the Kurt Canyon, you have the Orohondo shaft.
Yes.
That is the main exhaust shaft.
Okay.
So that links up everything from underground. Okay. So you've got Ross, Yates, they're the main intake shafts, so they bring down the fresh air.
Okay.
They push the fresh air through the caverns.
Okay.
And then the Orohondo will suck up the hot air or the dirty air out, and then eventually out to the Orohondo. Okay. So at the moment, we're pushing out around about 300,000 cubic feet per minute going up the Orohondo.
Okay.
Yeah. Sorry. Going up the raise bore.
May I have more than one?
Yeah, because it's such a good question.
We just have time for one more question, and I think this person want to make sure you get a chance.
Thank you. So I'm a rookie to this. Why lead? And I can speculate 2 reasons: because of the existing open cut, but also the distance from Chicago. Would that be appropriate?
I don't think so. I think a lot of it is to do that there was existing underground infrastructure. I know there was a lot of other mines that were under selection. It's a long time before my time. But I do know there was probably half a dozen sites, then narrowed down, and then eventually they picked, Lead, South Dakota, because of the existing mining infrastructures. Please.
So it was described to me that we were the Goldilocks. We weren't too far. We weren't too close. We were just right.
A fantastic end to an awesome presentation. Thank you so much. And if you have more questions, feel free to stick around. There's a little more swag. Thank you all for coming out tonight. Our next Deep Talks is an update from SURF. It's on April 4th. Same thing, free beverages and beer starting at 5 o'clock, free food and beverages. We hope you all come out for that as well. We certainly welcome everyone in the community, everyone in the Black Hills. Thank you all for a wonderful evening. Have a great night.